So I'm going to be talking about Clash, which is a tool for using Haskell for FPGA design. And if you don't know what Clash is, and if you don't know what FPGAs are, we're going to go into that. And then we're going to see how, if only you can count up, that already unlocks a whole world of exciting and fun things. So first of all, what are FPGAs and how does Clash figure into it? So if you look at any digital integrated circuit, and if you look really, really closely, you see that it's very regular. It's just a bunch of transistors that are connected together. And if you look at another digital IC and you zoom in, you also find it is nothing but transistors wired together. So it turns out that the only difference between different chips is how the transistors are wired together. But it's interesting because that suggests that if you want to make a new chip, all you need to do is you need to specify how the transistors, like if you have a bag of transistors, then how are they connected? And transistors are interesting because out of two transistors you can make a NAND gate, and NAND gates are universal. Like this is an example of a full adder, but I mean, don't look at the details. The point is that it's like something that expresses some meaningful function. And anything you think of as a function over bits can be expressed using, for example, NAND gates. By the way, so let me just go back for a second. So on my homepage, I have the slides. You can download them. And the reason I'm mentioning this is because depending on time constraints, we might have to skip some stuff. But the slides themselves really do contain all the details that we will have, including all the Haskell code that we will need to implement something fun. So not only can you use these NAND gates to implement any pure function from bits to bits, you can also create stateful circuits by implementing some kind of feedback. So this is an example of a flip-flop where you store the D input and emit it as the Q output, and whenever the clock is strobed, that's when we remember the input. So this is interesting because that means now we can make circuits that change over time. And this is all you need, right? Like if you have a way of expressing arbitrary functions and you have a way of sequencing with a state, what else could you possibly need to do anything? So we're going to make some abstractions because it would be quite cumbersome to design everything at this super lowest level. Like we as humans don't want to be wiring together individual NAND gates. So we're going to say that, okay, well, we're going to abstract over wire width. So if you can have, parallel wires, and we will think of them as something as a single wire of multiple bits. Similarly, instead of storing single bits in registers, we're going to have a whole array of registers and have multi-bit registers. And for the Boolean functions themselves, instead of wiring together individual NAND gates, we're going to look up tables. And also, we're going to use synchronous circuits, which means that the same clock is going to be connected to many registers. In fact, in this talk, all registers are always going to be in a single clock, because that means we don't really care about the details of what happens between two clock cycles. So what is an FPGA? An FPGA is something that allows you to express your circuits at this level of abstraction and then map it onto an array of these lookup tables where the connections between them are electronically configurable. So in this picture, like you see the white boxes would be these lookup tables and registers, and you see these interchanges in between them, and then if you configure an FPGA, you set each interchange and you set the contents of each lookup table. And so basically what it gives you is equivalent or like analogous to having your own chip fab, the chip factory, but it's like on your desktop, you press a button and you get a new chip. And so the way you program these, or the way you design these, is at the level of abstraction called the register transfer level model, where we say, okay, so we have these registers, we already established that they can be arbitrarily sized, and we have some combinational circuit, and we feed back the output of the register to the same register, or other registers, like you can have a network of these blocks. And yeah, and that's how you think of these designs. So that's the level where you want to specify them. And so what Clash is using Haskell as the language for specifying the RTL level design, or the RTL design of your FPGAs or other circuits. So the basic building blocks is that it gives you a type called signal, which corresponds to like a time-varying signal. And it's an applicative functor, which gives you a way of combining these signals with other signals and with the combinational circuits that correspond to pure functions. And then to do the actual feedback, you do guarded recursion using this register primitive. And so this is the example from the previous slide of the simplest possible example where you have register and via some pure function you feed it back. So this is how you would write this in Clash. You would just see that, so y0 is the initial value of y, and it's defined recursively, but the recursion is guarded by register, which is how Clash will know that what you really mean is that the next cycle's value of y is going to be the current cycle's value of y and some x input, and you feed these into this pure function. So, okay, so this is all nice, but what does it actually look like? So here's an example of I think one of the simplest stateful circuits you can think of, which is to just count up. So suppose we want to count up to 800. This is what the Clash code looks like. So we say that our externally visible type is just a signal that will contain a type called index 800. So this is the type of numbers between 0 and 799. And internally, it's defined recursively over register. It starts at 0, and then we apply this function called countSuck on the register's value. CountSuck is not suck from the enum type class, because that one doesn't really define what should happen at overflow. Like, we want our counter, when it gets to 799, we want it to go back to 0. So we use this counter type class provided by Clash, which specifies that it will overflow back to 0. And it also has the important property that you can detect, so types that implement this type class, they can also tell you when they overflow. We will see in a moment why that is important. But on its own, if we do this, so what are some interesting things here? So we see that this hidden clock reset enable constraint, it just means that Clash will hook up all the reset and all the clock lines behind the scenes for you, because otherwise a lot of your code is going to be just routing the same clock everywhere. And index 800 is an interesting type if you're not used to, like, modern Haskell with index types, because it's like the 800 is in the type level. But that just means that this is the type that goes from 0 to 799. So it will compute the number of bits required to do that, because we're building hardware. So it's not like, oh, we use 8 or 16 or whatever bit ins. We can use as little or as much as we want. So for index 800, we're going to just use 10 bits. So, okay, so what if we want to do something a bit more complicated? What if we want to count to 524 and 800? So this is where it comes into play that since the counter type class can detect overflow, that means it can be closed over products. So if you want a pair of two indices, you can, when you increment it, if the last one overflows, then you increment the first one by 1. So it's the usual, it goes from 0, 0, 0, 1, 0, 2, 0, 799, 1, 0, 1, 2, 1, 799, and so on. And we use this unbundle function here. That's not really that important. All it does is it goes from a signal containing a pair to a pair of signals. Okay, so now that we know how to count to 800, and now that we know how to count to 524, surely the next incremental step is to build a video game console. There's nothing in between in terms of complexity, right? That's the obvious next step. Draw the rest of the owl. So what does a video game console look like? Well, if you look at the dotted box, it has an input, a button, and then it has some video output. Okay, and what happens in between? Well, you have some game state that's going to be in some register, and then you feed it into some video signal generator circuit, and then you have the game logic, which updates the state. And so, of course, you only want to update the state at some regular, slow interval. So we will use the video output, the video generator's output, to detect the end of the frame. and we will update the game state only once per frame, as is usually done in video games. In fact, we can make it a bit simpler or nicer by saying that, okay, well, whether it's the new frame or not doesn't really meaningfully factor into the video game logic. It only factors into whether we allow the video game logic to update the register. Okay, so this is a nice design for a small video game console. What does it look like actually written down in Clash? Now I'm going to skip this slide and go to this one, which is the contents of the previous slide without some of the incidental complexity skipped, just for time. So basically we say that we write a function that goes from a bool-typed signal, which is whether the button is held down. Like, this is a game console with a single button input, right? And then we generate VGA output. And so internally, you see these two lines of code that correspond exactly to the picture that we have, the diagram we have drawn. So we say, okay, we have a register that is initialized with some initial state. It's enabled by the new frame signal. And whenever that new frame is true, we replace the contents of the state register with the result of applying the update state function on the button and the state. And where do we get the new frame signal? Well, we get it from the same source that we get the video output from, which is the video signal generator. Of course, at this point, we haven't written the video generator yet, and we haven't written update state yet. But this is just the outermost layer of our design. Okay, so then how do we generate video? Well, we need to take a bit of detour to understand what video even is. So let's talk about old CRT screens, like TVs, like this cathode ray tube, like the ones that are deep, not flat. So the way they worked, for those of you who are too young to remember, is that they basically scan the screen like the way you would type on a typewriter. So you go from your left to right, and then when you get to the end of the line, you get to the next line, and so on and so on. And so it scans the screen, and in any moment, the electron beam is focused at a certain point of the screen. So at the end. So then, if you change the intensity of your electron beam, you can draw, because it's going to be brighter or darker on the points as the electron beam scans it. Okay, so that means that if you want to draw something meaningful, all you need to know is you need to know in any given moment where the electron beam is, so you can change the intensity according to what you want to put there. Okay, this is grayscale video. If you want to do color, it's the same thing, but you have 3 intensities, red, green, and blue. Okay, so VGA is an old analog video format. It's nice to use because it was very widespread. So you can, you have no trouble even today finding screens that have VGA input. And they are very simple. Like, once you understand this model of the screen as this scanning thing. But it was designed for computers. So it's not like TV standards, which are all kinds of crazy because of backwards compatibility. So you have 3 separate channels for red, green, and blue, and you have horizontal and vertical sync signals. So what that means is that if you look at the signals that happen behind the scenes, you have so here the white is the thing you see on the screen. That's the so-called visible area. And then you see that there's some overhang, right? The purple overhang is what happens at the end of every line. So the electron beam has already left the screen, but there's still some time that it keeps going, basically. And then it gets a sync pulse from the computer, which tells it to go to the next line. And of course, all that takes time. And during this time, that's where the purple thing happens, the purple part happens. And then when you do it enough times, then you get to the bottom of the screen, and you enter the pink area, which is the vertical, non-visible part. And it's the exact same story. You keep drawing the lines, even though they are not visible anymore. And then you emit a vertical sync signal, which tells the TV or the monitor, the screen, to go back to the top. Okay, so this is what we want to do. Our computer that we implement on an FPGA, made out of individual, well, not individual NAND gates, but like these lookup tables, it needs to implement, first of all, these sync pulses at the right time. This is all about timing. So, okay, so you go and you look up in the big book of VGA mode descriptions, the timings for the mode that you want. So we want 640 by 480 because that's like the most standard VGA resolution. We do that at 60 frames per second. Okay, so we look it up and we find that, for example, the visible area is 25.422 microseconds. So you need to keep time for that long to know that you're in the visible part. And of course, you will want to subdivide that to know where exactly you are. And that sounds tricky. Like, how do you keep time for 25.422 microseconds? Like, where does that even come from? And vertical is the same. You want to wait for 15.253 milliseconds. Okay, so vertical timings are easy to understand because they are, like if you divide by a length of a horizontal line, of course it should divide evenly. And indeed they do. So we can, instead of using time, we can express the the vertical time in terms of lines. So for example, the visible area, no surprise there, is 480 lines. Well, that's what the mode claims to be. So of course it's going to be that much. And then, after that, you wait 11 more lines, then you produce the sync signal for 2 lines, and then you wait 31 more lines, and then you're back. Okay, so what about these weird microseconds? Well, it turns out it's all quantizable. It's quantized at 25.175 megahertz, which is again something you find in the description of the VGA format. So, so there's this concept called a pixel clock. And so if you run your pixel clock at 25.175 megahertz, then if you count to 640 plus 16 plus 96 plus 48, that's a whole line. You do that 480 plus 11 plus 2 plus 31 times, that's a full frame. Okay, so how do we do that? Well, so we want to produce these sync signals. And I already told you the number of pixels if you run at the right clock rate. So we want 800 pixels horizontal and we want 524 lines. But that sounds like we want to count to 524 and 800. Haven't we already done that? We have, right? So, oh, and one more thing. So of course, this only works if the clock domain that we're in, if the clock we're using, has exactly 25.175 megahertz. So we have to tell Clash that. Okay, so we already know how to do this, right? Because our horizontal and vertical sync signal can be computed by taking our counter from before and checking if it's between the start and the end of the sync, like those valleys. And that's just normal, pure functional Haskell programming. Something is between low and high if it's greater than or equal to low and less than or equal to high. Easy peasy, and this is a pure function, of course, because we are using the applicative function, or in this case, the functor instance of signal to apply it on the counter. And then we can write a function that either emits the low bit or the high bit, depending on whether we are in the valley or not. And different VGA formats might have like a high sync, but this one has a low sync. So that's why we parameterize sync with the polarity. Okay, so this gives us a way of describing a blank screen that is a valid VGA signal. Like you connect it to a screen, and like if it's a modern one, like a flat screen, it has VGA input, it will tell you that, okay, I detected this is 640 by 480, because it interprets the sync signals correctly. But there won't be any picture yet, because we haven't changed the RGB values yet. We haven't connected anything to that yet. So how do we do that? Well, to do that, we need to know where the electron beam at any given moment is. So our VGA driver will export or expose a pair of signals, the index into the x dimension and the index into the y dimension of where we currently are based on our internal timekeeping. And these are going to be maybe values, because if we are in the purple or the pink area, then there is no meaningful visible coordinate. Okay, so how do we do that? So we already seen how we generate the counters. We just need to strengthen them in the sense that if I have an index 800, I can turn that into maybe index 640 by returning just the same number if it's below 640, or nothing when it's above, right? This is the usual meaning of strengthening, because you have a more restricted type if you have a smaller size in your index type. So if we strengthen the horizontal and the vertical counter, that gives us the horizontal and the vertical visible coordinate. And that's it, right? So now that we have a way of generating the sync signals, and we have a way of knowing where we are, we just need to feed that to something that knows how to draw, and whatever comes out of that, we connect that into the RGB outputs. So that's exactly what we do here. So you see that there's this RGB input, and if you tell me the RGB position, then I know that the output should be either all zeros if it's not in the visible area, or it should be the color that comes out of the color that is fed into this. And where does that color come from? Well, it comes from applying some draw function, which we haven't written yet, on the current state and the currently scanned coordinate. And how do we know if it's a new frame? How do we know that we want to update the state? Well, that is easy, because the frame ends, conceptually, whenever the vertical coordinate becomes nothing, right? So if you think of the whole frame, all while you're drawing it, the y-coordinate is always a visible coordinate. It's just that the x might overrun onto the purple parts. But as soon as we enter the pink regime, we can say, okay, now we are done with the frame. So Clash has this combinator called isFalling, which basically says when the justness of the y-coordinate becomes from true to false, then it triggers. And then it will have to wait until it becomes true again, and then it becomes false again. And that's going to be the next time it fires. So it's the falling edge detection of the justness of the VGA-Y coordinate. And that's it. So we're going to use this framework to implement Flappy Bird. Except we're not really. We're going to implement Flappy Square because we're not going to bother with detailed graphics. And actually it's going to be more like crappy birds, because we'll see. Not all of it fits into the slides. So what is missing at this point? So we have made our video generator. We have connected it into our framework consisting of the register of the game state. Everything is done except anything that is specific to our game. So what remains? Well, we need some initial state that we initialize the register with. And actually, before we can even do that, we need to know what type our state is. Then we need a way to update that state, given the button press and the current state. And then we need to render the screen by taking the state, taking the visible coordinate, and of course, this only matters if we are inside the visible area, so there are no maybes anymore. Inside the visible area, give me the color of this particular pixel. Color here, by the way, I think I skipped over that, but color is just a triplet of bytes, okay? Because we use 8 bits per color channel, because why not? So, but notice one thing, which is that I could end my talk here, because all of these are now pure Haskell. There's no signals anywhere. So we're back to the well-known territory of just writing Haskell code. And that's one of the beauties of Clash, right? We needed to enter the world of signals because it's inherently stateful to count and to keep track of the electron beam and so on. But at this point, because we can use the abstractions of Haskell, and because we can use the applicative functor instance of signals to combine pure functions, to lift our pure functions into the combinational parts of our RTL, and because we can use custom data types, because it is a Haskell compiler, unlike the Lava family, here you can just use it, you can just make your own type. And then you can write your functions over your own type, which is exactly what we like to do in Haskell world, right? So let's see, just for illustrative purposes, so what that looks like for Flappy Square. So yeah, so I'm going to make some simplifications because we don't have much time. So we'll have a fixed looping level layout. The bird is going to be a square. The pipes are drawn with... Everyone knows what Flappy Bird is, right? I hope, okay. And when you die, we're just going to flash the background red for a single frame. Okay, so what is our game state? Well, it consists of the bird's position and the bird's vertical velocity. And then we also scroll the pipes, so we have to know how much we have moved horizontally, basically. And we also need to know whether we just died, because if we have, we want to flash the background red. So we define this data type. The usual thing is just a product type. And then, yeah, and we use some type. And you notice that we use signed 10, which is a 10-bit signed number, and we use index of some type level computation. So we always use, the right sizes, because we don't want to be wasteful. Because if you use like something that is 64-bit because you just use int, that means it's going to use 64 wires and 64 wide lookup tables. So it's like wasteful. You don't need to do that. Unlike in software where the processor has certain sized operations and that's all you get. And also, by using this index type, just like we've seen in the counter, the type can drive the behavior. So, when I make an index 800, it's different in semantics than an index 1000, even though both of them use 10 bits, right? Because if you add 1 to 799, you get 0, or you get 800. Okay, so... And then, like I said, one of the big simplifications we're going to do is that the pipes are going to be static. So it's going to loop the same pipes. So we have a vector of 4 pipes, and each pipe is represented as the top and the bottom coordinate, like how much it hangs down and how much, like stalactite, stalagmite, whatever. Okay, so let's start update state by moving the bird. So horizontally, it's easy to move the bird because it just moves by 1. That by definition, we just say that it scrolls at the speed of 1 pixel per frame, and the user has no control over it. The player has no control over it. But for vertically, we want to say that the y-coordinate changes by integrating the speed. And we use this trick here where the speed is shifted to the right by 3 so that we can have sub-pixel speeds, because otherwise even the smallest speed you can represent is 1 pixel per frame, and that's actually quite a lot. And then if you try to do anything more, then it's just gonna go out the screen very fast. So we want sub-pixel resolution for the speed. And so what is the speed? Well, the speed either decreases, basically, it either goes more and more down, which corresponds to gravity, or if the button is held, it flies up. Oh, this is another simplification compared to Flappy Bird, that instead of flapping, it's like a floaty bird. So it's like a crappy floating square. I feel like the title might have been a bit clickbaity, but whatever. And so, okay, so we update the state this way. And then the other thing we need to do is to end the game. So how do we know if we should end the game? Well, we need to check if the bird has hit the pipe, which means we need to know where is the pipe, the top and the bottom of the pipe, in the column that the bird is in, which is, of course, offset by the scroll, like how much we have scrolled horizontally. And so to do that, we need to, first of all, find the top and the bottom of the pipe at a given column. So this is what this pipe at function does. This is what we're going to look at next. And then the bird is clear if it's between the top and the bottom, plus a bit of adjustment because our bird is not a single pixel. It has height. So we represent the bird as its center, and then we add the height around it. So how do we know where the current pipe, the pipe that we are just passing through, how do we know which pipe that is? So basically what we do, so the thing we don't want to do is to compute modulus and division, because those don't really have a good way of doing it in small circuitry, especially if you want to do it in a single cycle combinational way. So instead of that, we choose the pipe width in pixels to be a power of 2. and then we choose the gap between, like how many, it's like no pipe, no pipe, no pipe, pipe, no pipe, no pipe, no pipe, pipes. Every fourth column is a pipe, and we chose every fourth, not every third or every fifth, because again, that's a power of 2. So that way, we can just take our x coordinate and chop it into 3 parts by just taking the bits apart. And if you think about hardware, taking the bits apart is not an operation. It's just a relabeling. It doesn't even need any circuitry because you have your, 640, so that's like 10 bits. You have your 10 wires coming in, and you just, okay, I'm going to call the bottom 6 wires this, and I'm going to call the next 2 wires this. So, okay, so we do that. And of course, for any given x coordinate and the state, we just add the x coordinate and the offset. So we can, for any column, we can compute the pipes, not just for where the bird is, because we want to use this for drawing as well. Okay, so we do this. We finally figure out the index of the pipe, and we just index into our vector of pipe lengths, and that's how we get the top and the bottom, because the pipes are represented as just a pair of these numbers. And if there is no pipe, so if we're in the gap, then we just return 0 and 480. Like there's nothing to hit. Okay, so now that we know how to update the state, how do we render this? So remember our draw function takes the state, takes the current electron beam coordinate, and gives you the color. Okay, so first thing we want to do is to say, if the xy coordinate is inside the bird, then it should be yellow. So when I say yellow, it's like defined somewhere as an RGB value, like whatever. So what does it mean to be inside the bird? Well, we know where the bird is. The bird has a fixed x position, because it like visually it doesn't move horizontally. And the y coordinate of the bird we know because it's part of the state. And then we just see if the given xy position is inside a square, like a bird width, bird height sized rectangle around that point. And if it is, then we are in the bird, so we should draw yellow. Okay, then we do the same for pipes. We return green if it's a pipe. Otherwise, we return blue, which is the background. And when it's game over, instead of blue, the background should be red. And that's why you get the flashing red background when you die. But then, it turns out that with really, really, really small effort, we can make the video output so much better looking. Because remember when we computed the pipe position, we dropped away the bottom 6 bits. But what if we don't? What if we return the offset? Then we know where in the pipe we are, and we can use this to basically use light green, dark green, or light green, green, or dark green to do like this 3D effect of pretending that the pipe has some. Okay. Okay. Cool. So this is the end result of this, and I'm gonna show it to you now. I'm gonna do the leap of faith of actually unplugging the HDMI cable and plug it into my FPGA. Okay, so now comes the tricky part where I try to get back to my slides. Wish me luck, because that is the part I have not tried. Okay, so this is what it looks like. Okay, so of course there are a lot. I'm going to skip over this, but like homework. Look at the slides, implement the homework for your own. Okay, so now comes the smartmanship part of this. I actually have a book about Clash. Retrocomputing with Clash, it's been getting quite good reviews, so I think I can recommend it to you without sounding too bad. We use Haskell and we use Clash to implement lots of old computers, and the culmination of it is that we actually build a full home computer, including the CPU, something you can plug into a keyboard and the screen and write your basic programs in. All 100% done in Clash. Okay, and that's basically it. So I think we have lots of time left for questions. So, yeah, thanks.
Great. So if anyone has a question, there's a microphone down here and also one up there. Yeah. That was great. That actually made me believe that I could write a game in Clash. Probably not.
So, yeah, good afternoon. Thank you so much. That was splendid. I trust you will forgive my pedantry for pointing out that in static CMOS, you need 4 transistors for a NAND gate or an OR gate. You only get an inverter with 2. That aside, that was tremendous. I'm doing functional programming every day and FPGAs every day, and I didn't know about Clash. That is absolutely outstanding. Thank you so much.
Thanks.
What quality do you find in the synthesized Verilog that you get from Clash compared to, say, a human doing the Verilog?
I would say it's quite good. So Clash, like, it's not a high-level synthesis language. It's not going to infer registers for you. Like, you have complete control over the synchronous nature of your circuit. And like, here's an example of, or here's the output of using Vivado to synthesize this for a Xilinx 7 series FPGA. I would say it's not too bad. Like, you can see, like, for example, there is a single 31-bit register, which is the game state. And if you add up, 10 bits of speed, 10 bits of acceleration, 10 bits of position, 10 bits of speed, and then the scroll offset, it really does come out to 31. So there's like no extra slack there. The 20-bit register comes from the VGA driver. Like, it's what you would expect if you, on paper, converted. And so, yeah, it's not wasteful in that sense. So there's not really a cost to the abstraction of using Clash versus handwriting Verilog, I would argue.
Marvelous. Thank you very much.
Yeah.
Yeah. You can either make your way across or down. Can everyone hear that microphone all right? It's difficult to tell from down here.
So, yeah, like, I can't hear much, but
cool.
yeah.
Okay.
So, thanks. That's a great result. But can you compare the code sizes of Clash and the generated Verilog or VHDL?
Well, I don't have it here. Like,
10 times smaller? 5
so
times?
The generated Verilog is like, it's not going to be huge because this is quite a simple circuit, right? It's just a bunch of comparators and like a couple of counters. So in this case, I would argue it's not like, the win is not so much in code size, it's in expressivity. Like because if you go back to like this, where was it? Just the beginning. Yeah, like this stuff, right? Like, you could even abstract this away. Like, you could write a Clash library that's parametric by the type of your game state and your game update function and your draw function, and that's a pattern you could abstract. So that's where the real win is, I would say. And also the fact that once you get over the video signal generator, the rest just becomes pure Haskell. So in this case, like, it wouldn't take much code to implement Flappy Bird in Verilog, but I would still argue that it wouldn't be as nice as the Haskell code you get to write to implement it.
Yeah, because in Verilog, for those who don't know it, or worse, in VHDL, there's lots of boilerplate, and you just look at the screen and scroll and scroll and scroll to see the actual logic.
Yeah.
And this looks much cleaner.
Yeah, and there are certain protections that gives you that Verilog doesn't, because this is something I skipped over because I didn't know how I was going to go on time. But the signal type constructor is indexed by the clock domain, so you can you can only combine signals that come from the same clock domain. So you never accidentally. Of course, there are like combinators to cross clock domains, but you're never accidentally crossing clock domains, and that's something that you don't get with VHDL or Verilog, as far as I know.
Thanks.
Yeah, go ahead.
So something that I didn't quite understand, is Clash an embedded DSL in Haskell, or you compile Haskell, you take Haskell source?
So Clash is a Haskell compiler. So you write your Clash code. That's why it's seamless to use things like custom data types and stuff. unlike the Lava family, which is a DSL, where you run your Haskell program, and when you run it, it emits the RTL, or the HDL. So no, this is a compiler.
Okay.
Any more questions? Otherwise, I have one.
Okay.
Yeah? Unless you want to say something?
No, I have one more extra slide.
I'm just wondering you seem like the type of person who's always trying to like tackle the next challenge, and you've got about 1 million things. What are you working on right now?
Oh, I'm not working on any of this. This is just hobby thing. This is unrelated.
But like, what are you playing with right now then?
Oh, so last week at ZuriHack, so this is all VGA output, right? But of course, these days it's HDMI that is the contemporary video standard. So last week at ZuriHack, I implemented a HDMI serializer all in Clash so that you can, so like this board, for example, it's actually emitting HDMI. So this is a composition of what you saw in the slides, which emits VGA plus a VGA to HDMI serializer.
Amazing.
But that's beyond the scope of the talk. So. Yeah, so if I have a bit more time, I want to mention one more thing, which is the testing story. So one cool thing about the fact that this is all Haskell, after you get, once you are finished with the video part, is that you can compile it as software Haskell. So here I have this window, which is an SDL application, and I can take the same update state and the same draw function and compile it not with Clash, but compile it with GHC, and hook it up with a simple SDL framework that just goes over your 640 by 480 numbers and calculates the color and fills an array with that, and then blitz it on the screen. So then the same code can be turned into an interactive, not quite real time because it's a bit slower, but like half real, like running at like 20 FPS interactive version of your circuit. So you can play on your computer the same Flappy Square circuit that you have written in Clash. And you can, so this allows you to test the logic of your game. But if you want to test, for example, the VGA signal generator, you can, Clash comes with a simulator. So it's very easy to take your Clash code and interact with it from software Haskell. So I also have a VGA signal interpreter, which also draws into SDL, but it draws whatever comes out of the VGA connector. So if you use that, you get end-to-end testing. Now that one, of course, is even slower. Like maybe you get like 3 frames per second, but it's still interactive. You can see it's much nicer way of doing things than writing like a Verilog or VHDL test bench ahead of time and then running it, because I can just literally press the button as long as I want, and then the bird flies up as long as I hold the button down. So, and of course you can use quick check on your circuits, because the logic part of it is just pure Haskell. And even for the stateful stuff, because there is a Clash simulator, so you can get like a stream of values, and then you can write your functional tests in terms of those. So I think that's a huge win to this approach.
Fantastic. We are out of time.
I take one question.
I'm
happy
sure
to take one more question.
And if anyone is desperate for lunch, feel free to go. You can go ahead and ask if people want to stay. And lunch will be like identical tables of stuff. So don't just join one big queue. There should be multiple smaller queues, and it's all the same food.
Right, so quick question, because you're essentially building an FRP network of the hardware. Have you looked at like adding ability to do time travel debugging to be able to debug not just the game logic, but the hardware portions?
So, okay, so I guess there's 2 ways of doing that. One would be to look at the stream you get out of the Clash simulator. Okay, so yes, you can do that, because one of the interfaces to the Clash simulator is an arrow machine. So it's like, it's a machine in the sense that, you get something where given the next input, it will give you the next output. And that's actually how the VGA signal interpreter-based simulator works, because we can't just run the simulator up ahead, because the whole point is that we want to feed back the input. So you can do clock cycle by clock cycle simulation such that you can determine the next input based on everything that happened so far. Interactively in this, like how do you, like coroutine-ly, if that makes sense. Yeah.